close your eyes for a moment. Not yet, but soon. First, I want you to imagine something impossible. Imagine nothing. Not darkness. Darkness is something. It's the absence of light, but it still exists within space. Not emptiness. Emptiness implies a container that could be filled. Not a void. A void is still a place where something could be. I mean nothing. No space, no time, no matter, no energy, no dimensions, no laws of physics, no mathematics, no possibility, no potential. Nothing. Your mind just failed, and that's okay. Every human mind fails at this task. We are creatures built from something, living within something, thinking with something. The concept of true nothing is as foreign to our brains as echolocation is to our eyes. We simply don't have the neural architecture to process it. And yet, if our best theories of cosmology are correct, this nothing, or something very close to it, is exactly what existed before the Big Bang. Or did it? Tonight we're going to explore the most profound question ever asked. A question that sits at the very edge of science, philosophy, and human understanding. A question that has haunted every civilization, every religion, every curious mind that has ever looked up at the stars and wondered, where did all of this come from? What existed before the Big Bang? Before I make a promise about what you'll discover tonight, I need to make a confession. No one knows the answer. Not me, not Stephen Hawking before he died, not any physicist alive today. This is genuinely unknown territory, the frontier where human knowledge dissolves into mystery. But here's what makes this question so extraordinary. We've gotten remarkably close. In the last century, we've pushed our understanding backward through time, further and further, closer and closer to that impossible moment when everything began. We've traced the history of the cosmos back 13.8 billion years. We've reconstructed the first minutes, the first seconds, the first fractions of a second after creation. We've approached the beginning. We've touched its edges. And what we've found there is strange beyond imagination. By the end of this journey, you'll understand what scientists actually mean when they talk about the Big Bang, because it's probably not what you think. You'll learn about the discoveries that revealed our universe's origin, from Einstein's reluctant equations to the accidental detection of creation's afterglow. You'll explore the limits of physics itself, the wall beyond which our mathematics breaks down and our theories fall silent. And you'll encounter the theories, real scientific theories proposed by serious physicists about what might have existed before. Eternal inflation, the multiverse, cyclic cosmologies, quantum fluctuations in nothingness, the collision of higher dimensional membranes. Ideas so strange they make science fiction look timid. If you enjoy these explorations into the deepest mysteries of existence, a like or subscribe helps others find these videos. Now, let your body relax, let your thoughts slow, and let's journey together to the very beginning and perhaps beyond.
The question haunts us. It has always haunted us. Every human culture, from the earliest civilizations to the most advanced technological societies, has created stories about the beginning. The ancient Egyptians believed the world emerged from the waters of chaos, called Nun, a dark, infinite ocean that existed before creation. The god Atum rose from these waters and spoke the world into existence. The ancient Greeks told of chaos, not disorder, but a yawning gap, a void from which Gaia, the earth, and Eros, the force of attraction, emerged. Before there was something, there was chaos. But what was chaos? They couldn't say. In Hindu cosmology, the universe cycles through endless creation and destruction, each cycle lasting 4.32 billion years. Before our current universe, there was another, and before that, another. Turtles all the way down, as the saying goes. The question of ultimate origin is deferred, pushed back through infinite regression. The Judeo-Christian tradition begins with the words, "In the beginning, God created the heavens and the earth." But theologians have debated for millennia what was there before the beginning. What was God doing before creation? St. Augustine, writing in the 4th century, gave a fascinating answer. The question is meaningless because time itself was created along with the universe. There was no before. Augustine, remarkably, anticipated by 1,500 years what modern physics would confirm. Time and the universe are inseparable. You cannot have a before the universe any more than you can have a location north of the North Pole. The question contains a hidden assumption that makes it incoherent. And yet, the question persists. It rises up from somewhere deep in human consciousness, immune to logical dismissal. Even if we accept that time began with the Big Bang, even if we acknowledge that before is a meaningless concept in this context, something in us keeps asking, yes, but what was there? This isn't stupidity. This is the human mind confronting its own limits and refusing to accept them. Why does this question haunt scientists? For most of human history, questions about the origin of the universe belonged to religion and philosophy, not science. Science dealt with how the world works now, not how it began. The beginning was too remote, too inaccessible, too wrapped in metaphysics to be a proper subject for empirical investigation. That changed in the 20th century. In 1915, Einstein published his general theory of relativity, a new description of gravity that replaced Newton's 200-year-old theory. Einstein showed that gravity isn't a force in the traditional sense, it's the curvature of space-time itself. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Einstein's equations were beautiful, powerful, and deeply unsettling. When he applied them to the universe as a whole, they seemed to imply something disturbing. The universe couldn't be static. It had to be either expanding or contracting. There was no stable middle ground. Einstein didn't like this. In 1917, he introduced a fudge factor, the cosmological constant, to force his equations to permit a static, eternal universe. He later called this his biggest blunder of his career. But the universe didn't care what Einstein preferred. In 1929, astronomer Edwin Hubble made one of the most important observations in scientific history. Using the 100-inch telescope at Mount Wilson Observatory, he measured the distances and velocities of dozens of galaxies. What he found changed everything. Almost every galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was expanding. If you run this expansion backward, like rewinding a film, galaxies get closer together. Space itself contracts. The universe gets smaller and denser and hotter. Run it back far enough, and everything converges to a single point. infinitely small, infinitely dense, infinitely hot. A singularity, a beginning. The implications were staggering. The universe had an origin. There was a moment, roughly 13.8 billion years ago, we now know, when everything that exists began. Space, time, matter, energy, the laws of physics themselves, all of it emerged from this primordial moment. The question that belonged to priests and philosophers suddenly belonged to physicists too. But scientists don't just ask questions, they demand answers that can be tested. And here's where the question of what existed before the Big Bang becomes so maddening. It may be fundamentally unanswerable. Here's why. Everything we know about the universe comes from information carried by light, radiation, particles, or gravitational waves. We look out at the cosmos and we see the past because light takes time to travel. The farther we look, the farther back we see. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all space, shows us the universe as it was about 380,000 years after the beginning. Before that, the universe was so hot and dense that photons couldn't travel freely. They were constantly absorbed and re-emitted, like light trying to pass through thick fog. So there's a wall, a curtain beyond which we cannot see using light. We call it the surface of last scattering. But we can push farther back using other methods. We can use our understanding of nuclear physics to reconstruct the first few minutes of the universe, when protons and neutrons fused to form the first atomic nuclei. We can use particle physics to model the first seconds when quarks combined to form protons and neutrons. We can use theories of high-energy physics to speculate about the first tiny fractions of a second, when the fundamental forces of nature separated from a unified whole. We've pushed back to about 10 to the minus 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1. A trillionth of a trillionth of a trillionth of a second. This number is called the Planck time, and it represents a fundamental limit. Before the Planck time, our physics breaks down completely. The equations of general relativity, which describe gravity, become incompatible with the equations of quantum mechanics, which describe everything else. Both theories are fantastically successful in their own domains, but in the extreme conditions of the earliest universe, impossibly small, impossibly dense, impossibly hot, they contradict each other. We need a new theory to describe what happened before the Planck time. We need a theory of quantum gravity. And despite decades of effort by thousands of brilliant physicists, we don't have one yet. So, when you ask what existed before the Big Bang, you're not just asking a hard question, you're asking a question that our current physics literally cannot answer. The tools we've built to understand reality break down at the very threshold we need to cross.
And yet scientists keep asking. They keep theorizing. They keep pushing. Because here's the thing about human beings. We don't accept mysteries. Not really. Not forever. Every question that once seemed unanswerable, what causes disease? What are stars made of? Why do species change over time? Eventually yielded to persistent inquiry. The unanswerable became answered. The mysterious became understood. Will this question be different? Is What existed before the Big Bang, the question that finally defeats us, the question where we must surrender and admit that some things are simply beyond human comprehension? Maybe that's a real possibility we have to hold in mind. But scientists have proposed ideas, real, serious, mathematically rigorous ideas about what might have preceded our universe. Some of these ideas are testable, at least in principle. Some make predictions we might one day verify. None are proven, all are speculative, but they represent humanity's best attempts to peer beyond the veil. We'll explore these ideas in depth tonight. Eternal inflation, where our universe is just one bubble in an infinite foam of constantly forming bubble universes. Cyclic cosmologies, where the Big Bang wasn't the beginning, but just the latest in an eternal series of bounces. The emergence of something from nothing through quantum fluctuation. The collision of higher dimensional membranes in the landscape of string theory. Each of these ideas has strengths and weaknesses. Each illuminates some aspects of the question while leaving others in shadow. And each is strange in ways that stretch our intuitions to the breaking point. But before we explore what might have come before, we need to understand what the Big Bang actually was, because I suspect what you've been told, what most people believe, is a cartoon version of a much stranger truth. The Big Bang was not an explosion. It did not happen at a point in space. There was no outside observer watching it occur. If these statements surprise you, good. They surprised me when I first learned them, and understanding why they're true is essential to understanding what the question, what existed before, actually means. So let's go deeper. In the next part of our journey, we'll reconstruct the Big Bang itself, what it was, how we know it happened, and why it was so different from anything our intuitions prepare us for. But for now, let this question sit with you. What existed before the Big Bang? The question might be meaningless. Time might have begun with the universe, making before a nonsense concept. The question might be unanswerable. The limits of physics might forever prevent us from accessing information about a pre-bang state. The question might have an answer we can never test. Some theories about pre-bang reality make no observable predictions, putting them beyond science's reach. Or the question might one day be answered. We might find evidence in gravitational waves, in subtle patterns in the cosmic microwave background, in the mathematics of a future theory of quantum gravity that tells us what came before. We don't know which of these possibilities is true, and that uncertainty itself is profound. We are creatures born in the middle of a story. The pages before our existence have been torn out. We've reconstructed some of them through incredible ingenuity and effort, but the first page, the very first page, remains hidden. Maybe it will always remain hidden. Or maybe, someday, someone will find a way to read it. For now, rest in the mystery. The universe is 13.8 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars. It operates according to laws of physics that are beautiful and strange and still not fully understood. And before all of it, before space, before time, before matter and energy and the laws themselves, there was something or nothing, or a question that makes no sense to ask. We don't know. And that's where our journey begins. Before we can ask what existed before the Big Bang, we need to understand what the Big Bang actually was.
And I need to warn you, almost everything you think you know about it is probably wrong. Let's start by destroying some myths. The Big Bang was not an explosion. I know, the name suggests an explosion. The word bang is right there. Every documentary you've ever seen probably showed an explosion, a bright flash in the center of a dark screen, debris flying outward, fire and chaos. Forget all of that. It's wrong. An explosion happens when something expands rapidly into the space around it. A bomb goes off and the shrapnel flies outward through the air, through the room, through the space that already exists. The explosion has a center, the point where the bomb was. The explosion has an edge, the expanding shell of debris, and the explosion happens within space that was there before the bomb detonated. The Big Bang was nothing like this. The Big Bang didn't happen at a point in space. It happened everywhere simultaneously. Every point in the universe was the center of the Big Bang, because the Big Bang was the expansion of space itself. Think about it this way. Take a balloon. Draw dots on the surface of the balloon with a marker. These represent galaxies. Now inflate the balloon. What happens to the dots? They all move apart from each other. From the perspective of any single dot, all the other dots are moving away. The more distant a dot is, the faster it seems to recede. But here's the crucial question. Where is the center of this expansion? Where on the surface of the balloon did the expansion start? The answer is nowhere, or everywhere. The expansion doesn't have a center on the surface. The surface itself is expanding. Every point on the surface is equivalent. No dot is more central than any other. This is analogous to what happened in the Big Bang. Space itself expanded. Every point in space moved away from every other point. There was no center, there was no edge, there was no outside. The Big Bang didn't happen at a location in the universe. The Big Bang was the universe, all of space, everywhere, expanding from an extremely hot, dense state. Here's another misconception. The Big Bang did not happen in empty space. There was no empty space waiting to be filled. Space itself came into existence. Before the Big Bang, there was no space for anything to exist in. No coordinates, no locations, no distances, no up, down, left, right, no here versus there. The concept is genuinely difficult to grasp because our brains evolved to navigate space. We think in terms of things existing at locations. We imagine the Big Bang as something that happened somewhere, but that somewhere didn't exist until the Big Bang created it. Space was born in the Big Bang. Every cubic centimeter of space that exists today, from the space between your eyes and this screen, to the space between galaxies, to the space in the farthest reaches of the observable universe, all of it emerged from that primordial expansion. And time. We need to talk about time. This is where things truly get strange. According to Einstein's general theory of relativity, space and time are not separate things. They're woven together into a single four-dimensional fabric called space-time. You can't have space without time. You can't have time without space. They're aspects of the same underlying reality. When the Big Bang created space, it also created time. Before the Big Bang, there was no before. I need you to sit with that statement for a moment, because it sounds like nonsense, but it's actually a precise physical claim. When we ask, what happened before the Big Bang, we're assuming that time extended backward before the Big Bang, that there was a timeline stretching into the past, and the Big Bang was an event on that timeline. But if time itself began with the Big Bang, then the question is malformed. It's like asking, what is north of the North Pole? You can walk north on Earth until you reach the North Pole, but once you're there,
The concept of north loses meaning. There's no further north to go. Every direction is south. Similarly, if you could somehow travel backward in time toward the Big Bang, you would approach the moment of origin, but you couldn't go further back because there was no further back. Time had an edge, a boundary, a beginning. Stephen Hawking liked to use this analogy. He said, asking what came before the Big Bang is like asking what is south of the South Pole. The question assumes the existence of something that isn't there. This doesn't mean the question is stupid. It means the question might be based on assumptions that don't apply to reality. Our intuitions about time, that it flows continuously, that it extends infinitely in both directions, that events always have prior causes, might simply be wrong when applied to the universe's origin.
So, what was the Big Bang? The Big Bang was a state, an extremely hot, dense, rapidly expanding state from which our universe evolved. It wasn't a moment when something appeared out of nothing. It was the earliest moment that our physics can describe. Let me take you through the first second of existence. And when I say first second, I mean something much stranger than you might imagine. The story begins at the Planck time, 10 to the minus 43rd seconds after the Big Bang. That's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 everyday experience. More time passes between one beat of your heart and the next than has passed in the entire history of the universe measured in Planck times. Before the Planck time, we don't know what happened. Our physics breaks down. General relativity and quantum mechanics contradict each other. We need a theory of quantum gravity to describe this era, and we don't have one. But at the Planck time and after, we can begin to piece together the story. At this moment, the observable universe, everything we can see today, including billions of galaxies spanning billions of light years, was compressed into a region far smaller than a proton. The temperature was about 10 to the 32nd degrees, 100 billion degrees. At this temperature, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe expanded and cooled, the forces began to separate. Gravity broke off first, becoming its own distinct force. Then the strong force separated. Then the electromagnetic and weak forces split from each other. These symmetry-breaking events released enormous amounts of energy, driving the expansion forward. Somewhere around 10 to the minus 36th seconds, something remarkable happened. The universe underwent a period of exponential expansion called cosmic inflation. In a tiny fraction of a second, perhaps 10 to the minus 32 seconds, the universe expanded by a factor of at least 10 to the 26th. That's a 1 followed by 26 zeros. Space expanded faster than light. This doesn't violate relativity because nothing was moving through space faster than light. Space itself was stretching. The speed limit applies to motion through space, not to the expansion of space itself. During inflation, the observable universe went from being smaller than a proton to being about the size of a grapefruit. And then inflation ended, and the energy driving it was converted into a hot soup of particles and radiation. This is sometimes called the hot Big Bang, the moment when the universe became filled with the matter and energy that would eventually form stars and galaxies and planets and people. By 1 microsecond after the Big Bang, the universe had cooled enough
for quarks to combine into protons and neutrons. These are the particles that make up atomic nuclei. By 1 second after the Big Bang, the universe had cooled to about 10 billion degrees. Electrons and positrons, particles of matter and antimatter, were annihilating each other in vast numbers, converting their mass into pure energy. For reasons we don't fully understand, there was a tiny asymmetry, slightly more matter than antimatter. This small surplus is why anything exists at all. If matter and antimatter had been exactly balanced, they would have annihilated completely, leaving a universe of pure radiation with no atoms, no stars, no planets, no life. By 3 minutes after the Big Bang, the universe had cooled to about 1 billion degrees. Now, protons and neutrons could fuse together without being immediately blasted apart by the intense heat. This was the era of Big Bang nucleosynthesis. In the next 20 minutes or so, about 25% of the ordinary matter in the universe was converted into helium. Small amounts of lithium and deuterium were also formed, but the expansion and cooling happened too quickly for heavier elements to form. The universe remained mostly hydrogen and helium. Then, for 380,000 years, not much happened. The universe was a hot plasma, a soup of free electrons and atomic nuclei, so hot that electrons couldn't bind to nuclei to form neutral atoms. Light couldn't travel through this plasma. Photons were constantly scattered by free electrons, bouncing around like light in a thick fog. But the universe kept expanding and cooling, and at about 380,000 years, the temperature dropped below 3,000 degrees, cool enough for electrons to finally bind to nuclei. Hydrogen and helium atoms formed, and suddenly, the universe became transparent. The light that was trapped in the plasma was released. It streamed freely through space for the first time. That light is still traveling today. It has been stretched by the expansion of the universe from visible light into microwaves. It fills all of space, coming from every direction. We call it the cosmic microwave background radiation, and it is the oldest light in the universe, the baby picture of creation.
How do we know any of this is true? This is a reasonable question. We're talking about events that happened 13.8 billion years ago, events that no one witnessed, events that took place in conditions we can barely imagine. How can we claim to know what happened? The answer is that the Big Bang theory makes predictions, specific, testable predictions that have been confirmed again and again. First, the expansion of the universe. If the Big Bang happened, then space has been expanding ever since. We should see distant galaxies moving away from us, with more distant galaxies receding faster. This is exactly what Hubble discovered in 1929, and every observation since has confirmed it. The universe is expanding, and the rate of expansion tells us when the expansion began, about 13.8 billion years ago. Second, the cosmic microwave background. If the universe was once a hot plasma that became transparent at 380,000 years, then the light released at that moment should still be detectable today, stretched by expansion into microwaves.
In 1964, Arno Penzias and Robert Wilson accidentally discovered this radiation while working on a radio antenna in New Jersey. They found a faint hiss of static coming from every direction in the sky, corresponding to a temperature of about 2.7 degrees above absolute zero. They had detected the afterglow of creation. The CMB has been mapped with exquisite precision by satellites like COBE, WMAP, and Planck. These maps show tiny variations in temperature, 1 part in 100,000, that revealed the seeds of cosmic structure. The slightly denser regions in the early universe eventually grew through gravity into galaxies and galaxy clusters. The slightly less dense regions became the voids between them. The patterns in the CMB match the predictions of Big Bang theory with stunning accuracy. The heights of the peaks, the positions of the troughs, the statistical properties of the fluctuations, all of it fits. Third, the abundance of light elements. If the Big Bang happened, then nucleosynthesis in the first few minutes should have produced a specific ratio of hydrogen, helium, and lithium. The universe should be about 75% hydrogen, 25% helium, and trace amounts of lithium and deuterium by mass. We can measure these abundances by studying the oldest stars and the most pristine gas clouds. The results match the predictions beautifully. The ratio of hydrogen to helium is exactly what Big Bang nucleosynthesis predicts. These three pillars, expansion, the CMB, and light element abundances, provide overwhelming evidence that the Big Bang happened. The theory isn't speculation, it's not a guess, it's one of the best confirmed theories in all of science.
And yet, the Big Bang theory doesn't tell us what came before. It describes the evolution of the universe from an extremely hot, dense state. It doesn't explain where that state came from. It's like a movie that starts in the middle of a scene. We can follow the plot forward from that point, but the opening is missing. The first reel is gone. We know the universe was very hot and very dense 13.8 billion years ago. We know it has been expanding and cooling ever since. We know the process that led to stars, galaxies, planets, and life. But we don't know why the expansion started. We don't know where the energy came from. We don't know why the laws of physics are what they are. We don't know if time really began at the Big Bang, or if something came before. These are the questions that haunt cosmologists. These are the questions we'll explore in the rest of our journey. But for now, let this sink in. You are made of matter that was forged in the first minutes of the universe. The hydrogen in your body has existed since the Big Bang. The atoms in your cells are 13.8 billion years old. You are not separate from the cosmos. You are the cosmos, evolved into a form that can ask questions about its own origin. Rest in that thought. Feel the ancient matter that composes you, and know that when you ask what came before, you are the universe asking about itself.
The story of how we discovered the Big Bang is one of the greatest detective stories ever told. It spans a century. It involves some of the most brilliant minds in human history, and it's filled with wrong turns, lucky accidents, and moments where the universe seemed to be actively hiding its secrets. Let's go back to the beginning of this story. not the beginning of the universe, the beginning of our understanding. The year is 1915. The place is Berlin, and a 36-year-old physicist named Albert Einstein is about to change everything. Einstein had already revolutionized physics once with his special theory of relativity in 1905. That theory showed that space and time were relative, that clocks run at different rates depending on how fast you're moving, that objects contract in the direction of motion, that mass and energy are interchangeable. It was radical, beautiful, and deeply unsettling to classical intuitions. But special relativity had a limitation. It only applied to objects moving at constant velocities. It couldn't handle acceleration or gravity. Einstein spent the next 10 years trying to extend his theory to include these phenomena. The result was the general theory of relativity, published in November 1915. It was his masterpiece. The theory described gravity not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. Massive objects like the sun bend the fabric of space-time around them, and smaller objects like planets follow curved paths through this warped geometry. The equations of general relativity were elegant and powerful. They explained anomalies in Mercury's orbit that Newton's theory couldn't account for. They predicted that light would bend as it passed near massive objects, a prediction spectacularly confirmed during a solar eclipse in 1919, making Einstein an international celebrity. But the equations also implied something troubling. While Einstein was tinkering with his equations in Europe, a young astronomer in America was making observations that would overturn the static universe forever. Hubble was working at Mount Wilson Observatory in California using the most powerful telescope in the world, the 100-inch Hooker telescope. His goal was to study the mysterious spiral nebulae that dotted the sky. These fuzzy patches of light had been cataloged for centuries, but no one knew what they were. Were they clouds of gas within our own Milky Way galaxy? Or were they something else entirely? In 1924, Hubble made a breakthrough. By identifying a special type of star called a Cepheid variable in the Andromeda Nebula, Hubble was able to calculate its distance. Cepheid variables pulsate with a regular rhythm, and the period of pulsation is directly related to the star's intrinsic brightness. By comparing how bright the star appeared to how bright it actually was, Hubble could calculate how far away it must be. The answer was staggering: about 900,000 light-years. This was far beyond the boundaries of the Milky Way, which was thought to be only about 100,000 light-years across. Andromeda wasn't a nebula within our galaxy. It was a galaxy in its own right, an island universe containing billions of stars separated from us by a vast gulf of empty space. The universe had just gotten much, much bigger. But Hubble wasn't done. Over the next few years, he measured the distances to dozens of galaxies, and he noticed something peculiar. Almost all of them showed a redshift in their light. Let me explain what this means. When an object moves away from you, the light waves it emits get stretched out. Longer wavelengths correspond to redder colors. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound lower pitched as it drives away from you. The more redshifted a galaxy's light was, the faster it was moving away from us. And when Hubble plotted the redshifts against the distances, he found a stunning relationship. The farther away a galaxy was, the faster it was receding. This wasn't random motion. This was a pattern. The entire universe was expanding. Hubble published his findings in 1929. The paper was only 6 pages long, but its implications were revolutionary. If the universe was expanding, then it must have been smaller in the past. Run the expansion backward and everything converges. There was a moment
when all the matter in the universe was compressed into an incredibly small, hot, dense state. There was a beginning. When Einstein learned of Hubble's discovery, he was initially skeptical, but after visiting Mount Wilson and seeing the evidence firsthand, he accepted it. He removed the cosmological constant from his equations, calling it his greatest mistake. Ironically, decades later, astronomers would discover that the cosmological constant, or something very like it, does exist. The universe's expansion is actually accelerating, driven by a mysterious, dark energy that behaves almost exactly like Einstein's discarded fudge factor. His biggest blunder turned out to be right, after all.
By the 1940s, a theoretical framework for the Big Bang was beginning to take shape. The physicists George Gamow and his colleagues Ralph Alpher and Robert Herman worked out the physics of the early universe. They calculated how protons and neutrons would fuse in the first few minutes to form helium and other light elements. They predicted the ratios of hydrogen to helium that should exist in the universe if the Big Bang had occurred. And they made another prediction, one that would prove crucial. If the universe had started in an extremely hot, dense state, then it must have been filled with intense radiation. As the universe expanded and cooled, this radiation would have been stretched along with space itself. Gamow's team calculated that this primordial radiation should still exist today, filling all of space, but cooled by the expansion to just a few degrees above absolute zero. They predicted that the universe should be glowing faintly in microwaves, the remnant heat of creation. But detecting this radiation was beyond the technology of the 1940s. The predictions sat in the scientific literature, largely forgotten, for nearly 2 decades. In 1964, 2 radio astronomers at Bell Telephone Laboratories in New Jersey were wrestling with a problem. Arno Penzias and Robert Wilson were trying to use a horn-shaped radio antenna originally designed for satellite communication for astronomical observations, but they couldn't get rid of a persistent hiss of static. No matter where they pointed the antenna, no matter what time of day or year, there was always a faint background noise. They checked everything. They rebuilt parts of the antenna. They discovered that pigeons had been nesting inside the horn and removed them, carefully cleaning out what Wilson delicately called a white dielectric material, pigeon droppings. The noise persisted. The static was coming from every direction in the sky, uniformly. It corresponded to a temperature of about 3.5 degrees above absolute zero. Penzias and Wilson were baffled. Meanwhile, just 40 miles away at Princeton University, a team led by physicist Robert Dicke was building an antenna specifically to search for the cosmic microwave background radiation. They knew about Gamow's prediction. They knew what the afterglow of the Big Bang should look like. They were racing to find it. Then they got a phone call from Penzias. Penzias had heard through a colleague that the Princeton group was interested in cosmic background radiation. He described the persistent noise that he and Wilson couldn't eliminate. Dicke immediately realized what they had found. Penzias and Wilson had accidentally discovered the cosmic microwave background, the oldest light in the universe. They had detected the afterglow of the Big Bang. When Dicke hung up the phone, he turned to his colleagues and said, "Well, boys, we've been scooped." The discovery was published in 1965. Penzias and Wilson received the Nobel Prize in 1978. Their accidental finding
provided the most direct evidence that the Big Bang had actually occurred. The universe had a beginning, and we could see its light.
But the cosmic microwave background held far more secrets than anyone initially realized. The CMB, as detected by Penzias and Wilson, appeared perfectly uniform, the same temperature in every direction. This was expected if the early universe was hot and dense, with radiation thoroughly mixed. But it was also a puzzle. If the early universe was perfectly uniform, how did galaxies form? Gravity can amplify small differences in density, but it needs something to work with. There had to be tiny variations in the early universe, slightly denser regions that would eventually become galaxies, slightly less dense regions that would become voids. For decades, astronomers searched for these variations. Ground-based and balloon-based experiments pushed toward greater sensitivity, but the variations remained hidden. Then, in 1989, NASA launched a satellite specifically designed to map the CMB with unprecedented precision. It was called the Cosmic Background Explorer, COBE. COBE measured the CMB from space, above the interfering atmosphere. And in 1992, the team announced their results. They had found the variations. The CMB wasn't perfectly uniform after all. There were tiny ripples, temperature differences of about 1 part in 100,000. Slightly warmer spots and slightly cooler spots distributed across the sky in a pattern that matched theoretical predictions. These ripples were the seeds of cosmic structure, the slightly denser regions of the early universe that would grow over billions of years into galaxies and galaxy clusters. We were seeing the baby picture of the cosmos, complete with the faint features that would become everything. George Smoot, the lead scientist on COBE, described the discovery as like seeing the face of God. The Nobel Prize followed in 2006. But COBE was just the beginning. In 2001, NASA launched a more sophisticated satellite called the Wilkinson Microwave Anisotropy Probe, WMAP. Over 9 years of observations, WMAP mapped the CMB with 35 times the resolution of COBE. The results were extraordinary. The patterns in the CMB contained information about the fundamental properties of the universe. By analyzing the sizes and distributions of the hot and cold spots, cosmologists could determine the age of the universe, 13.8 billion years, its geometry, flat within measurement precision, its composition, 5% ordinary matter, 27% dark matter, 68% dark energy, and many other parameters. WMAP transformed cosmology from a field of rough estimates into a precision science. We went from knowing the age of the universe to within a few billion years to knowing it within 50 million years. Then, in 2009, the European Space Agency launched Planck, the most sensitive CMB satellite yet. Planck's resolution was another factor of 3 better than WMAP. It measured the CMB with exquisite precision, detecting features that no previous instrument could see. The Planck results, released in 2013 and refined in subsequent years, confirmed and sharpened the WMAP findings. They revealed subtle details about inflation,
the period of exponential expansion in the first fraction of a second. They constrained theories about the early universe with unprecedented accuracy. Each generation of instrument has peeled back another layer of the mystery. Each has brought us closer to the beginning, and yet each discovery has also revealed the limits of what we can know. The cosmic microwave background shows us the universe at 380,000 years old, the moment when it first became transparent. We cannot see any earlier using light because the universe was opaque before that moment. Other methods let us push back further. The abundances of light elements tell us about the first few minutes. Theoretical models extend our understanding back to tiny fractions of a second. But there's a wall, the Planck epoch, 10 to the minus 43 seconds after the Big Bang, is where our physics fails. Beyond that wall, we have only speculation. The next generation of experiments aims to peer even closer to the beginning. Gravitational wave detectors might someday detect ripples from the inflationary epoch. New telescopes might find subtle signals from processes that occurred before the CMB was released. But the ultimate question, what came before the Big Bang, may require a revolution in physics to answer. It may require a theory of quantum gravity that we haven't yet discovered. The history of cosmology is the history of pushing back the frontier of ignorance. Each generation has learned more than the last. Each has gotten closer to the beginning. But the beginning itself remains shrouded, and what came before remains the deepest mystery of all.
We've traced the history of the universe back 13.8 billion years. We've mapped the cosmic microwave background, the afterglow of creation released when the universe was 380,000 years old. We've used nuclear physics to understand the first few minutes when hydrogen and helium were forged. We've pushed our theories back to tiny fractions of a second after the Big Bang. But there's a wall, a boundary beyond which our physics cannot penetrate, a threshold where our most successful theories break down, contradict each other, and fall silent. This is the edge of knowledge, and tonight I want to take you there. The wall has a name, the Planck epoch. It's defined by a moment in time 10 to the minus 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1. A number so small that it makes the blink of an eye seem like an eternity. A number so small that there's no physical process we've ever observed that happens this quickly. This timescale is called the Planck time, named after the German physicist Max Planck, one of the founders of quantum mechanics. The Planck time isn't arbitrary, it emerges naturally from the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When you combine these constants in a certain way, you get a set of natural units, the Planck units. There's a Planck length, about 1.6 times 10 to the minus 35 meters, roughly 100 million trillion times smaller than a proton. There's a Planck mass, about 22 micrograms, tiny by everyday standards, but enormous compared to subatomic particles. There's a Planck temperature, about 1.4 times 10 to the 32 degrees, hot beyond imagination. And there's the Planck time, the time it takes light to travel one Planck length, about 5.4 times 10 to the minus 44 seconds.
These aren't just convenient units for calculation. They represent fundamental limits. At scales smaller than the Planck length, our concepts of space and distance lose meaning. At timescales shorter than the Planck time, our concept of time itself becomes fuzzy. At the Planck temperature, quantum effects and gravitational effects become equally important, and our physics falls apart. Before the Planck time, the universe was smaller than the Planck length and hotter than the Planck temperature. And here, at this threshold, we encounter the deepest problem in theoretical physics.
The problem is this: we have two extraordinarily successful theories of physics, and they don't work together. The first theory is general relativity, Einstein's masterpiece. General relativity describes gravity as the curvature of space-time. It explains the motion of planets, the bending of light around stars, the expansion of the universe, and the behavior of black holes. It's been tested to extraordinary precision, and it's never been wrong. The second theory is quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales. It explains atoms, molecules, chemical reactions, semiconductors, lasers, and the fundamental particles that make up everything. It's the foundation of modern technology. And like general relativity, it's been tested to extraordinary precision and has never been wrong. But when you try to combine them, when you try to create a quantum theory of gravity, the math explodes. Here's the issue. In quantum mechanics, empty space isn't really empty. It's a seething foam of virtual particles, constantly popping in and out of existence. These quantum fluctuations happen everywhere, all the time, at every point in space. Now, according to general relativity, energy causes space-time to curve. If empty space is filled with quantum fluctuations, then those fluctuations should curve space-time. And when you try to calculate how much curving there should be, you get infinity. Not a large number, infinity. This is called the problem of non-renormalizability, and it means that our naive attempt to combine general relativity and quantum mechanics gives nonsensical answers. The theories contradict each other at the Planck scale. In normal situations, this isn't a problem. Gravity is incredibly weak at small scales, so we can use quantum mechanics without worrying about gravitational effects. And at large scales, quantum effects average out, so we can use general relativity without worrying about quantum fluctuations. The two theories work in different domains, and they don't conflict in practice. But at the Planck scale, both effects are important. Quantum fluctuations are violent, and gravitational effects are strong. You can't ignore either one, and you can't use both theories together. This is why we can't describe the universe before the Planck time. Our physics literally breaks down. We don't have the mathematical tools to describe what was happening.
Let me try to convey what this breakdown means. Imagine you're a historian trying to reconstruct the past. You have documents from the 20th century, detailed records that let you understand events year by year, sometimes day by day. You have documents from the Middle Ages, less detailed but enough to reconstruct the broad outlines. You have fragments from ancient Rome and Greece. You have hints from prehistoric times, fossils, artifacts, cave paintings. The further back you go, the less information you have, but you can still piece together a story. You can still make reasonable inferences. Now imagine you hit a wall, a point in the past where all your methods of investigation stop working. where the very concepts you use to think about history, cause and effect, chronological sequence, events happening in time, cease to apply. That's what happens at the Planck epoch. It's not just that we lack data, it's that our conceptual framework, the framework of events happening at specific times in a continuous space-time, may not apply. At the Planck scale, space-time itself may become fuzzy, foamy, uncertain. The smooth fabric of space and time that we take for granted may dissolve into quantum chaos. Time itself may cease to be a meaningful concept. This isn't just ignorance, it's a breakdown of the categories we use to think. At the heart of the Planck epoch lies something even more troubling: the singularity. If you take the equations of general relativity and run them backward, tracing the expansion of the universe in reverse, you reach a point where all the matter and energy is compressed into a single point, a point of infinite density, infinite temperature, infinite curvature, a point where space-time itself is infinitely twisted. This is the singularity, the mathematical point from which the Big Bang supposedly emerged. But here's the thing: singularities are not real. They're signs that a theory has broken down. When a theory predicts infinity, it's telling you that it's being pushed beyond its domain of validity. It's like a map that shows roads going off the edge of the page. The roads don't actually end, the map just doesn't cover that territory. General relativity predicts a singularity at the beginning of the universe, but this prediction almost certainly doesn't reflect reality. It reflects the limits of general relativity. As you approach the Planck scale, quantum effects become important. General relativity, which ignores quantum effects, gives increasingly wrong answers. The singularity is the wrongest answer of all, a sign that the theory has completely failed. What actually happened at the beginning of the universe? We don't know. To find out, we need a theory that works at the Planck scale, a theory of quantum gravity. For decades, physicists have been searching for a theory of quantum gravity. Several candidates have been proposed, each with passionate advocates and significant challenges. String theory is perhaps the most famous approach. It proposes that the fundamental entities in the universe aren't point particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. In string theory, gravity emerges naturally as one of the vibrational modes, a particle called the graviton. String theory is mathematically elegant, and it automatically includes gravity in a consistent quantum framework. But it comes with baggage. The theory only works if the universe has extra dimensions, typically 10 or 11 dimensions, instead of the 4 we observe. These extra dimensions would have to be curled up so small that we can't detect them. String theory also has an enormous number of possible solutions, perhaps 10 to the 500 different configurations, each corresponding to a different possible universe with different physical laws. This landscape of possibilities makes it difficult to extract specific predictions that could be tested. Loop quantum gravity takes a different approach. Instead of adding extra dimensions or new entities like strings, it tries to quantize space-time itself. In loop quantum gravity, space is made of discrete chunks, tiny loops woven together into a network called a spin foam. Space isn't continuous, it's granular, like pixels on a screen, but at the Planck scale. Loop quantum gravity makes interesting predictions about what happens at the Big Bang singularity. In some versions of the theory, the singularity is resolved. Instead of infinite density, there's a bounce, where a previous contracting universe transitions into our expanding one. The Big Bang isn't the beginning, it's a transformation. Other approaches include causal set theory, which proposes that space-time is fundamentally discrete, a set of points with causal relationships between them. And there are various attempts to modify either quantum mechanics or general relativity to make them compatible. None of these theories is complete. None has made predictions that have been definitively tested. We don't know which approach, if any, is on the right track. What we do know is that we need something new. General relativity and quantum mechanics, magnificent as they are not the final word. The universe knows physics that we haven't discovered yet.
And this is why the question, what existed before the Big Bang, is so difficult. It's not just a question about history. It's a question about the nature of space and time themselves. If time began with the Big Bang, then asking what came before is like asking what's north of the North Pole. The question assumes something that doesn't exist. But maybe time didn't begin with the Big Bang. Maybe our classical concept of time, smooth, continuous, flowing from past to future, is just an approximation. Maybe at the Planck scale, time is different, fuzzy, granular, or perhaps entirely absent. Some theories suggest that before the Big Bang, time was something else entirely. Perhaps there was only space, a four-dimensional space instead of a 3 + 1-dimensional space-time. Perhaps time crystallized out of this primordial space as the universe cooled. Stephen Hawking and James Hartle proposed something like this in the 1980s. Their no-boundary proposal suggested that if you trace the universe back to its origin, time gradually transforms into a spatial dimension. The universe has no boundary in the past, no edge, no beginning point. Just as the surface of a sphere has no edge, you can walk on a sphere forever without ever reaching a boundary. In this picture, asking what came before the Big Bang is meaningless in the same way that asking what's north of the North Pole is meaningless. The question contains a false assumption. But this is just one proposal among many. We don't know if it's correct. Let me be honest with you about where we stand. We are at the edge of human knowledge. We have pushed our understanding to extraordinary limits. We can describe the universe with precision back to fractions of a second after its origin. We can explain the formation of atoms, the birth of stars, the evolution of galaxies, the emergence of life. But the very beginning remains hidden. Not because we haven't looked, not because we lack curiosity or intelligence or resources, because our physics breaks down, because the tools we've built to understand reality reach their limits, because the universe was once in a state so extreme that our categories of thought, space, time, cause, effect may not apply. This is humbling, but it's also exhilarating. We are the first generation of humans to push this far. Our ancestors could only wonder and tell stories.
We have equations and observations and satellites mapping the afterglow of creation. And we're not done. Physicists are working on theories of quantum gravity. Cosmologists are searching for traces of the pre-Planck epoch in the patterns of the CMB. Gravitational wave detectors might someday detect ripples from the inflationary epoch, or even earlier. The wall may not be permanent. It may just be the frontier of our current understanding, waiting to be pushed back. But for now, we rest at the edge. We've come so far, and what lies beyond is still unknown.
Now we arrive at the heart of our journey. We've established what we know. The universe began 13.8 billion years ago in an extremely hot, dense state. We've traced how we discovered this truth. We've confronted the wall, the Planck epoch, where our physics breaks down. But scientists don't simply accept walls. They climb them, tunnel through them, or find ways around them. And despite the limits of our current physics, brilliant minds have proposed theories about what might have existed before the Big Bang. None of these theories is proven. All of them are speculative. Some may be untestable in principle, but they represent humanity's best attempts to answer the deepest question we can ask. Let's explore them together.
Theory 1. Nothing. The simplest answer to what existed before the Big Bang is nothing. Not empty space, not a vacuum, not darkness waiting to be filled with light. Absolute nothing. No space, no time, no matter, no energy, no laws of physics, no mathematics, no potential, no possibility. True nothing. This is, philosophically, the most radical answer. It suggests that the universe came into existence from a state of complete non-being, that existence itself had a beginning, not just the matter and energy, but the very framework of reality. Many people find this idea incoherent. How can something come from nothing? Doesn't there have to be something for the Big Bang to happen in? Doesn't there have to be a cause? But our intuitions about causality and existence are built from everyday experience. They evolved to help us navigate a world of objects and events, predators and prey, causes and effects. There's no guarantee they apply to the origin of reality itself. In everyday life, every event has a cause, but the Big Bang may not be an event in the ordinary sense. It may be the beginning of the very framework within which events and causes exist. Asking what caused the Big Bang may be like asking what's north of the North Pole, a question that seems meaningful but isn't. Some philosophers and physicists have embraced this radical answer. Perhaps the universe simply began. Perhaps there is no deeper explanation. Perhaps existence is a brute fact, something that simply is without prior cause or reason. This is unsatisfying to many people. We want explanations. We want to understand why there is something rather than nothing. But the universe is not obligated to satisfy our desires for explanation. Reality may be fundamentally mysterious at its root. Still, most scientists prefer theories that offer some kind of explanation, even if that explanation pushes the mystery back one more step, and several such theories have been proposed.
Theory 2. Eternal inflation. One of the most influential theories about what preceded our Big Bang is eternal inflation. It's a natural extension of cosmic inflation, the period of exponential expansion that occurred in the first fraction of a second of our universe. Let me remind you what inflation is. In standard Big Bang cosmology, there's a puzzle. How did the universe become so uniform? When we look at the cosmic microwave background, we see that the temperature is the same in all directions, to about 1 part in 100,000. But in the early universe, regions on opposite sides of the sky were never in contact with each other. Light didn't have time to travel between them. So how did they know to have the same temperature? Inflation solves this problem by proposing that the universe underwent a period of incredibly rapid expansion in its first moments. Regions that are now on opposite sides of the observable universe were once close together, close enough to reach thermal equilibrium before inflation stretched them apart. Inflation is driven by a hypothetical field called the inflaton field. When this field is in an unstable high-energy state, it causes space to expand exponentially. Eventually, the field rolls down to a lower energy state, inflation ends, and the energy is converted into the hot matter and radiation of the Big Bang. Here's where it gets interesting. In the theory of eternal inflation, the inflaton field doesn't decay everywhere at once. Instead, it decays randomly in different regions at different times. Imagine a vast ocean of inflating space with bubbles of non-inflating space forming here and there. Each bubble is a separate universe with its own Big Bang, its own history, its own eventual galaxies and stars. And here's the key. The inflating space between the bubbles expands so fast that it always stays ahead of the bubble formation. No matter how many bubbles form, there's always more inflating space being created. The process never ends. In eternal inflation, there was no beginning. The inflationary process has been going on forever, or at least the question of its beginning becomes murky. Our universe is just one bubble in an infinite, eternal foam of bubble universes. This doesn't quite answer the question of what came before our Big Bang, but it reframes it. Our Big Bang was the moment when our local patch of inflating space decayed into a hot, expanding universe. Before that, there was the inflationary process, which may have no beginning at all. The eternal inflation scenario has profound implications. If true, there are infinitely many universes out there, each with its own Big Bang, perhaps with different physical constants, different particles, different laws, the multiverse. We'll explore this more in the next part of our journey.
Theory 3. The cyclic universe. What if the Big Bang wasn't the beginning? What if it was just the latest in an eternal series of cosmic cycles? The idea of a cyclic universe is ancient. Hindu cosmology describes vast cycles of creation and destruction, each lasting billions of years. The Stoic philosophers of ancient Greece believed the universe was periodically destroyed and reborn in identical form. Modern physics has given these ideas new life. In the 1930s, shortly after the discovery of cosmic expansion, physicist Richard Tolman proposed that the universe might oscillate, expanding from a Big Bang, reaching a maximum size, contracting to a big crunch, and then bouncing back in a new Big Bang.
But Tolman's model had a problem. According to the laws of thermodynamics, entropy, disorder, always increases. Each cycle would have more entropy than the last. The cycles wouldn't be identical. They would gradually wind down, like a bouncing ball that bounces lower each time. And if you traced the cycles backward, you'd still reach a first cycle, a true beginning. In 2001, physicists Paul Steinhardt and Neil Turok proposed a new kind of cyclic model that avoided this problem. Their theory drew on string theory and the concept of extra dimensions. In string theory, our universe might be a three-dimensional brane, short for membrane, floating in a higher dimensional space. Other branes might exist parallel to ours, separated by a small gap in the extra dimension. Steinhardt and Turok proposed that our Big Bang occurred when two branes collided. The collision released enormous energy, creating the hot, dense state we call the Big Bang. The branes then separated, and our universe expanded and cooled. But the branes are attracted to each other. Eventually, they drift back together and collide again, another Big Bang. The cycle repeats endlessly. In this model, the entropy problem is avoided because entropy is diluted during the long expansion phase between collisions. Each cycle can begin in a low entropy state, just like the last one. The cyclic model is elegant, but it has challenges. It relies on string theory, which is itself unproven, and it makes predictions that are difficult to distinguish from those of inflationary models. Still, the idea of a cyclic universe offers a compelling alternative to a unique beginning. Perhaps there was no first moment. Perhaps the universe has always existed, cycling through big bangs and expansions for all eternity.
Theory 4. A universe from nothing. In 1982, physicist Alexander Vilenkin proposed one of the most audacious ideas in cosmology. The universe might have appeared from literally nothing through a process called quantum tunneling. In quantum mechanics, particles don't have definite positions. They're described by probability waves, and there's always a small chance of finding a particle in an unexpected location. This leads to a phenomenon called tunneling. A particle can tunnel through a barrier that classical physics says is impenetrable. This isn't science fiction. Quantum tunneling is real and well tested. It's essential for nuclear fusion in stars. It's used in scanning tunneling microscopes. It's a routine part of electronics. Vilenkin proposed that the universe itself might have tunneled into existence from nothing, not from empty space, from absolute nothingness. No space, no time, no matter, no energy. In his model, there's a small but non-zero probability of a tiny closed universe, a universe with finite size and no boundary, spontaneously appearing. Once it appears, inflation takes over, and the tiny seed expands into a vast cosmos like ours. This idea sounds absurd. How can something come from nothing? But Vilenkin argued that nothing is unstable in quantum mechanics. The very laws of quantum physics, if they can be said to exist in some sense prior to the universe, imply a probability of universes appearing. The physicist Lawrence Krauss popularized a related idea in his book, A Universe from Nothing. Krauss emphasized that in quantum field theory, the vacuum, the lowest energy state of the fields, is not truly empty. It's seething with virtual particles, constantly being created and annihilated.
Perhaps, Krauss suggested, the universe itself is an enormous quantum fluctuation, a bubble of space and time that popped into existence and, instead of disappearing again, inflated and became our cosmos. Critics have pointed out that this isn't really nothing in the philosophical sense. The quantum vacuum still has properties. It still obeys the laws of quantum mechanics. Nothing in physics isn't the same as nothing in philosophy. But perhaps that's the point. Perhaps true philosophical nothing is incoherent. Perhaps there's no way for reality to be completely absent. Perhaps existence is, in some sense, necessary, and the quantum vacuum is the minimal form that existence can take. The universe from nothing is a deeply strange idea. It challenges our intuitions about causality, existence, and the relationship between something and nothing. But it's taken seriously by physicists, and it represents one possible answer to our question.
Theory 5. Conformal cyclic cosmology. The physicist Roger Penrose, one of the greatest mathematical minds of our time, has proposed his own theory of what came before the Big Bang. He calls it conformal cyclic cosmology, or CCC. Penrose starts with a remarkable observation. The Big Bang and the far future of the universe have something in common. At the Big Bang, the universe was extremely hot and dense. Particles were moving at nearly the speed of light. At such extreme temperatures, particles are effectively massless. Their kinetic energy so dominates their rest mass that mass becomes irrelevant. In the far future, the universe will be extremely cold and empty. Stars will burn out. Black holes will evaporate. Eventually, the only things left will be photons, particles of light, which are massless and travel at light speed. Here's the key insight. For massless particles, time doesn't pass. Photons experience no time between emission and absorption, no matter how far they travel. From a photon's perspective, the entire history of the universe happens instantaneously. Penrose realized that the physics at the Big Bang and the physics of the far future are mathematically similar. Both are dominated by massless particles. Both are scale invariant. They look the same at any size. He proposed that the far future of one universe smoothly becomes the Big Bang of the next. The conformal structure of space-time, the structure that remains when you forget about distances and remember only angles, is preserved across the transition. One aeon ends and another begins. In CCC, there is no true beginning and no true end. Each aeon gives birth to the next in an eternal sequence. Our Big Bang was the end of a previous aeon, a previous universe that expanded and cooled until nothing remained but massless particles and smooth, empty space. Penrose has even claimed to find evidence for CCC in the cosmic microwave background. He and his colleagues have identified circular patterns in the CMB that they interpret as the imprints of black hole collisions from the previous aeon, gravitational waves that somehow survived the transition between aeons. Most cosmologists are skeptical. The statistical significance of these patterns is disputed, and CCC makes assumptions about physics at the end of the universe that are difficult to verify. But the theory is beautiful in its elegance. It connects the beginning and the end, the Big Bang and the heat death, into a single eternal cycle. It suggests that our universe is neither the first nor the last, just one chapter in an endless story.
Theory 6. Brain collision in string theory.
String theory proposes that the fundamental entities in the universe are not point particles, but tiny vibrating strings of energy. The theory requires extra dimensions, typically 10 or 11, beyond the 3 spatial dimensions and 1 time dimension we experience. In some versions of string theory, our observable universe is confined to a 3-dimensional brane, a membrane floating in higher dimensional space. Other branes may exist parallel to ours, separated by a tiny gap in the extra dimensions. We encountered this idea earlier in the context of the cyclic universe, but brane cosmology offers other possibilities too. One idea is the ekpriotic scenario, proposed by Steinhardt, Turok, and others. In this model, our Big Bang was caused by a collision between our brane and another brane moving through the extra dimensions. Before the collision, both branes were cold and empty, or at least very different from the hot, dense state of the Big Bang. The collision itself generated the enormous energy that we identify as the Big Bang. Our brane was suddenly filled with hot matter and radiation, and it began to expand. In this picture, time existed before the Big Bang. The branes had their own histories, moving through the extra dimensions, approaching each other slowly. But those histories are inaccessible to us. We can only observe our brane. The other brane and the higher dimensional space between them are hidden. Another possibility is that branes can spawn from other branes. Our universe might have budded off from a parent brane, inheriting some of its properties but developing independently. In this case, the parent brane existed before our Big Bang and may still exist today, floating somewhere in the higher dimensional bulk. Brane cosmology is highly speculative. String theory itself has not been experimentally confirmed. The extra dimensions have never been detected, and the idea of branes colliding or budding is extremely difficult to test. But it represents one way that modern physics imagines what might have preceded the Big Bang, a higher dimensional reality that we cannot directly observe, within which our universe is embedded like a slice of bread in a loaf.
Theory 7. The multiverse. Many of the theories we've discussed, eternal inflation, the cyclic universe, brane cosmology, imply the existence of other universes beyond our own. If eternal inflation is correct, our universe is one bubble among infinitely many, each with its own Big Bang, its own history, perhaps its own physical constants. If the cyclic model is correct, there have been previous universes before ours, and there will be more after. If the brane cosmology is correct, other branes may host other universes entirely. This is the multiverse. Not just one universe, but an enormous, possibly infinite ensemble of universes. The multiverse is controversial. Some physicists embrace it as the natural consequence of our best theories. Others reject it as unscientific, since we may never be able to observe other universes directly. But if the multiverse is real, then the question, what existed before the Big Bang, has a clear answer: other universes. The multiverse has always existed, generating new universes eternally. Our universe is not the first or the only, just one among countless many. This doesn't quite solve the ultimate mystery. we can still ask, where did the multiverse come from? What is the deeper reality that generates universes? What are the ultimate laws that govern the whole? Perhaps these questions have answers. Perhaps they don't. Perhaps the multiverse itself is the bedrock reality, and asking what came before it is like asking what's north of the North Pole.
Let me step back and summarize what we've explored. We've encountered theories where the Big Bang emerged from true nothing. Existence appeared without prior cause. Eternal inflation, an endless process of universe spawning. A cyclic bounce, the end of a previous universe. Quantum tunneling, a fluctuation from the void. A previous aeon, the far future of an earlier cosmos. Brain collision, an event in higher dimensional space. The multiverse, an eternal ensemble of all possible worlds. Each of these theories is speculative. Each has strengths and weaknesses. Each makes predictions that are, at best, extremely difficult to test. And they may all be wrong. The true answer to what existed before the Big Bang may be something we haven't imagined yet, something so strange that our current concepts can't capture it. What should we make of this landscape of possibilities? I think we should be humble. We are creatures of limited understanding, using tools built for everyday life to probe the deepest mysteries of existence. It would be remarkable if we got the right answer on the first try. But I also think we should be proud. The fact that we can even ask these questions, that we can formulate rigorous mathematical theories about the origin of reality, is extraordinary. No other species on Earth, as far as we know, has ever done this. We are the universe wondering about itself. And the fact that we don't yet have the answer doesn't mean we never will. The history of science is the history of impossible questions becoming answered. What are stars? We know now. What is the universe made of? We know now. How old is the cosmos? We know now. What existed before the Big Bang? We don't know yet, but someday we might.
Of all the ideas we've explored tonight, none is more mind-expanding or more controversial than the multiverse. The notion that our universe might be just one among countless others, perhaps infinitely many, stretches the imagination to its breaking point. It challenges our sense of uniqueness, our intuitions about reality, and even our understanding of what science can and cannot tell us. Let's go deeper into this strange territory. The modern concept of the multiverse emerges naturally from eternal inflation, the theory we touched on earlier. Recall the basic idea. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion driven by a field called the inflaton. This inflation explains why the universe is so uniform. Regions that are now on opposite sides of the sky were once in contact before inflation stretched them apart. But here's what makes eternal inflation special. The inflaton field doesn't decay everywhere at once. Imagine the inflaton field as a ball rolling down a hill. When it reaches the bottom, inflation ends and the energy is released as heat, the hot Big Bang. But in eternal inflation, the hill is bumpy and irregular. The ball might get stuck in little valleys or roll slowly through flat regions. Different parts of the field decay at different times. Now add one more ingredient. While the field is inflating, space is expanding exponentially fast. So fast that even as some regions decay and stop inflating, the regions that are still inflating grow faster than the decay can spread. The result is an infinite, self-sustaining process. Bubbles of non-inflating space form. These are individual universes, each with its own Big Bang, but the inflating space between them keeps expanding faster than the bubbles can fill it. New bubbles form constantly, forever. In this picture, the multiverse is like an infinite ocean of expanding space dotted with bubble universes that appear spontaneously and continuously. Our universe is one such bubble. It formed 13.8 billion years ago when our local patch of inflating space decayed. But before our bubble formed, other bubbles had already appeared, and after our bubble formed, infinitely more have followed. There is no edge to this process, no beginning, no end, just eternal inflation, spawning universes without limit.
If this is true, how many universes are there? The answer depends on what version of eternal inflation you consider, but in many models, the number is infinite. Not just a large number, literally infinite. An endless collection of bubble universes, each as real as our own. This is almost impossible to wrap your mind around. We can barely comprehend the size of our own observable universe. Billions of galaxies, each containing billions of stars. Now multiply that by infinity. And it gets stranger. In an infinite multiverse, everything that can happen does happen somewhere. Every possible configuration of atoms, every possible history, every possible outcome of every possible event, all of it is realized in some bubble universe. There are universes where Earth never formed, universes where dinosaurs never went extinct, universes where you made a different choice this morning and your life took a completely different path. There are universes almost identical to ours, differing only in the position of a single atom. And there are universes radically different, with alien physics and unrecognizable structures. If the multiverse is truly infinite, then there are infinitely many copies of you, living infinitely many variations of your life, scattered across an endless foam of bubble universes. This is not mysticism. This is a logical consequence of eternal inflation, taken seriously by many physicists. But perhaps even more remarkable than the sheer number of universes is the possibility that they might have different physics. In our universe, the laws of physics have specific values: the strength of gravity, the mass of the electron, the speed of light, the charge of the proton. These values determine everything: how atoms form, how stars burn, how chemistry works, how life is possible. But why do these constants have the values they do? This is one of the deepest questions in physics, and we don't have a satisfying answer. One possibility, suggested by string theory and other approaches, is that the constants are not fundamental. They might emerge from deeper structures,
the way strings vibrate, the shape of hidden dimensions, the configuration of fields. And if these deeper structures can vary, then different universes might have different constants. In the multiverse, each bubble universe might have its own physics. Some might have stronger gravity. Some might have lighter electrons. Some might have forces we've never heard of. Some might have no forces at all. Most of these universes would be barren. If gravity is too strong, stars collapse into black holes before they can shine. If the nuclear force is too weak, atoms can't form. If the cosmological constant is too large, space expands so fast that galaxies never coalesce. Only a tiny fraction of possible universes would allow complexity, chemistry, and life. And here's the key insight. We necessarily find ourselves in one of those rare, life-permitting universes. We couldn't exist in a universe where atoms don't form or stars don't shine. Our existence is evidence that we're in a hospitable bubble. This is called the anthropic principle. It doesn't explain why the constants have the values they do, but it explains why we observe those particular values. We observe them because we couldn't exist to observe anything else.
The anthropic principle is controversial. Some physicists embrace it as a natural consequence of the multiverse. If there are infinitely many universes with different constants, then of course we find ourselves in one compatible with our existence. There's no mystery to explain, just selection bias. Others reject this reasoning as giving up on explanation. Science, they argue, should explain why the constants have their values, not just note that we happen to be in a universe where we can exist. Invoking the multiverse feels like admitting defeat. The debate is intense and unresolved. But notice what's at stake. If the multiverse is real and the anthropic principle is the answer to fine-tuning, then our universe is not special. It's not designed. It's not the product of a plan. It's just one random bubble among infinitely many, and we're here because, well, where else could we be? This is humbling in a way that earlier scientific revolutions were humbling. Copernicus showed that Earth is not the center of the solar system. Darwin showed that humans are not separate from the animal kingdom. The multiverse, if true, shows that our universe is not unique, just one of countless variations, most of which are empty and dead. But is the multiverse science? This is a serious question, and thoughtful people disagree. Science, traditionally, is about making predictions and testing them against observations. A theory is scientific if it can be falsified, if there are observations that could, in principle, prove it wrong. The multiverse poses a challenge to this framework. If other universes are forever beyond our reach, if no signal, no message, no evidence can ever travel between bubble universes, then how can we test whether they exist? Some physicists argue that the multiverse is not science at all, but metaphysics. It may be true, but we can never know. It makes no testable predictions. It's a matter of faith, not evidence. Others disagree. They point out that eternal inflation does make predictions about our universe. Predictions about the patterns in the cosmic microwave background, about the statistics of cosmic structure, about the distribution of matter on large scales.
If these predictions are confirmed, that's evidence for inflation, and eternal inflation is a natural extension of inflation. There's also the possibility of detecting bubble collisions. If another bubble universe formed close enough to ours, the two bubbles might have collided in the past. Such a collision would leave a signature, a circular bruise in the cosmic microwave background, a region where the temperature is slightly different from the rest. Cosmologists have searched for these signatures. So far, no definitive evidence has been found, but the search continues. Even if we never detect another universe directly, the multiverse might still be the best explanation for what we observe. Sometimes in science, we accept the existence of things we can't see because they're implied by theories that explain what we can see. We don't observe atoms directly, but we accept their existence because atomic theory explains chemistry. Similarly, we might accept the multiverse because eternal inflation explains the uniformity and flatness of our universe. This is philosophically subtle territory. Reasonable people disagree about whether the multiverse counts as science. But the debate itself is illuminating. It forces us to think carefully about what science is, what explanation means, and how we should reason about things beyond our direct experience.
Let's step back and contemplate what the multiverse would mean for our place in reality. If the multiverse is real, then we are even smaller than we thought. Our planet is a mote of dust orbiting an ordinary star in an ordinary galaxy in an ordinary corner of one bubble universe among infinitely many. But there's another way to see it. If the multiverse is real, then existence is vastly richer than we imagined. Reality isn't just this one cosmos with its particular history and particular laws. Reality is an endless flowering of possibilities, an infinite tree of branching universes exploring every configuration that physics allows. We are one expression of this infinite creativity, one way the multiverse has organized itself into complexity and consciousness, one perspective on an endless tapestry. And if there are infinitely many versions of you out there, making infinitely many choices, living infinitely many lives, then perhaps your individual choices still matter. They matter to you, in this branch, in this moment. The multiverse doesn't diminish your experience, it multiplies it. Or perhaps none of this is true. Perhaps the multiverse is a beautiful speculation that will be swept away by future discoveries. Perhaps our universe really is unique, the only one existing for reasons we haven't yet understood. We don't know, and that's okay. The multiverse reminds us that reality might be far stranger and far larger than we can imagine. It's a hypothesis at the frontier of knowledge, where science meets philosophy and speculation meets mathematics. Whether or not it's true, thinking about it expands our minds and humbles our certainties. As you lie here tonight, consider this. You might be the only version of you in all of existence, a unique and unrepeatable event in a singular cosmos. Or you might be one of infinitely many, each living their own version of this moment, scattered across an endless multiverse that has no beginning and no end. Either way, you are here. You are conscious. You are contemplating the deepest mysteries that reality has to offer. That's extraordinary, whichever version of the story turns out to be true. We've traveled so far together now, through the birth of our universe, through the minds of the greatest thinkers who ever lived, through theories so strange they make science fiction seem pedestrian. Cyclic universes bouncing through eternity, quantum fluctuations birthing realities from nothing, multiverses containing every possible version of every possible thing, consciousness as the fundamental fabric of existence. And now, we must ask the hardest question of all. Will we ever actually know? Will humanity ever pierce the veil that hangs over that first moment? Will we ever see beyond the cosmic horizon that separates our universe from whatever came before? Or are we forever trapped on this side of creation, pressing our faces against the glass, watching our own reflection stare back? Let's think about this carefully, because the answer is more complicated and more beautiful than you might expect. The limits of observation. There's a fundamental problem with studying the pre-Big Bang era, and it's not a technological limitation. It's not that we don't have powerful enough telescopes or sensitive enough detectors. It's deeper than that. The cosmic microwave background, that ancient light we've discussed, represents a wall in time. Everything before that moment, before the universe became transparent, is hidden from us. We can calculate backward, we can model, we can theorize, but we cannot see. And the Big Bang itself? If it truly represents the beginning of space and time as we understand them, then asking what came before may be asking a question that has no meaning, like asking what's north of the North Pole. The question assumes a framework that simply doesn't apply. This is what physicists call a horizon problem, not a technological barrier, a fundamental barrier, built into the very structure of reality. But here's where it gets interesting, because throughout the history of science, we have repeatedly encountered barriers that seemed permanent and then found ways around them.
The history of the impossible. Consider the atom. In the 19th century, many physicists believed we would never directly observe atoms. They were simply too small. The wavelength of visible light was too large to resolve them. It seemed like a fundamental limit built into the physics of light itself. And yet, we found ways. Electron microscopes, scanning tunneling microscopes. Today, we can image individual atoms. We can move them one by one. We can write words in xenon atoms on copper surfaces. What seemed impossible became routine. Consider black holes. For decades, they were purely theoretical objects. Einstein himself doubted they could exist in nature, and even those who believed in them assumed we would never actually see one. The event horizon, by definition, lets no light escape. How do you photograph something that emits no light? And yet, in 2019, the Event Horizon Telescope captured an image of the supermassive black hole at the center of galaxy M87. We photographed the unphotographable. Consider the beginning of the universe itself. When Lemaitre proposed his primeval atom, when the idea of a cosmic beginning first entered physics, many scientists assumed we would never have evidence. How could we possibly observe something that happened billions of years before Earth existed? And yet, the cosmic microwave background, primordial element abundances, the pattern of galaxies across the sky, evidence everywhere we look of those first moments. What seemed impossible
became the foundation of modern cosmology. So, when someone tells you we will never know what came before the Big Bang, remember this history. Remember how many nevers have become, of course we did. New windows on reality. And we're not done opening windows. Gravitational wave astronomy is barely a decade old. Already it has shown us colliding black holes, merging neutron stars, events completely invisible to traditional telescopes. Could gravitational waves from the pre-Big Bang era still be rippling through our universe? Some theories suggest primordial gravitational waves born in the first trillionth of a second might carry information about conditions during or even before the Big Bang. We're building detectors to find them. LISA, the Laser Interferometer Space Antenna, will be a gravitational wave detector in space. 3 spacecraft separated by millions of kilometers, forming a triangle larger than the Earth, listening for whispers in space-time itself. Could those whispers carry news from before time began? Particle physics continues to advance. The Large Hadron Collider recreates conditions from the first moments after the Big Bang. Every collision is a tiny window into that primordial fire. And new accelerators are being planned, more powerful, more precise. What might they find? Evidence of extra dimensions? Particles from before the bang? Hints of the bounce that preceded our universe? We don't know. That's why we keep looking.
The theoretical frontier. Meanwhile, theorists continue their work. The search for a theory of quantum gravity, a framework that unifies quantum mechanics with general relativity, remains the great quest of fundamental physics. And several candidates exist. String theory, with its vibrating loops and hidden dimensions, offers one path. It naturally incorporates cosmological scenarios where universes are born from colliding brains or eternal inflation. Loop quantum mechanics, with its discrete spacetime and quantum geometry, offers another. It provides concrete mechanisms for the big bounce, calculations we can actually perform. Causal set theory, with its fundamental grains of spacetime, approaches from quantum information theory, treating reality as a vast computation. Each path might lead to testable predictions. Each might open windows we cannot yet imagine. We are not at the end of physics. We are not even close. We are perhaps at the end of the beginning. What we do know. Let's step back for a moment. Let's appreciate how far we've come. A century ago, we didn't know the universe had a beginning. We didn't know there were other galaxies. We didn't know about the cosmic microwave background, or the expansion of space, or the first 3 minutes of creation. Now, we can describe those first 3 minutes in exquisite detail. We know the temperature of the universe when it was 1 second old. We know the ratio of hydrogen to helium forged in that primordial fire. We know the pattern of sound waves that rang through the infant cosmos. We have reconstructed the first 380,000 years of cosmic history, minute by minute, temperature by temperature, process by process. That is extraordinary. That is a triumph of human curiosity. And the question of what came before, the mystery that remains, is not a failure. It's an invitation. It's the next horizon, the next great adventure for minds yet unborn.
The philosophical dimension. But perhaps the deepest answer to will we ever know lies beyond science. Perhaps it lies in what we're really asking. When we ask about before the Big Bang, we're not just asking about physics. We're asking about meaning. We're asking about origins. We're asking the questions that humans have always asked, around fires under ancient skies. Why is there something rather than nothing? Why does existence exist? What is the ground of being itself? These questions may not have scientific answers, not because science is limited, but because the questions themselves might transcend the categories that science uses. Science explains how things work, why anything works at all, why there is a things and a works may be a different kind of question. Philosophers call this the meta-question, and throughout human history it has been answered in different ways, through religion, through mysticism, through art, through the simple act of living fully and not demanding answers the universe is not obligated to provide. Perhaps the mystery is not a problem to be solved. Perhaps it is a wonder to be contemplated. The gift of not knowing. Consider this. If we knew exactly what came before the Big Bang, if we had a complete, final, absolutely certain theory, something would be lost. The mystery would be solved. The question would be closed. And we would face the universe as a puzzle that had been finished, a book that had been read, a journey that had been completed. But that's not where we are. We're in the middle of the story. The greatest story ever told, the story of where everything came from, is still being written. By physicists working through equations on blackboards, by engineers building instruments that stretch the boundaries of the possible, by observers peering at the faintest signals from the most distant sources, and by you, right now, lying in the dark, wondering. That wondering is not a weakness. That wondering is what makes us human. The universe gave rise to creatures who would look back at it and ask, "Where did you come from?" The cosmos created beings who would try to understand the cosmos. And in that trying, in that reaching, something beautiful happens. We participate in the mystery. We don't just exist in the universe. We are the universe trying to understand itself. A final thought. 13.8 billion years ago, something happened. We call it the Big Bang, but that name captures nothing of its strangeness, its impossibility, its wonder. From whatever came before, from the void or the bounce, or the quantum foam, or the eternal inflation, or the mind of God, or pure mathematics, or something we have not yet imagined, our universe was born. And in that universe, on one small planet, around one ordinary star, in one unremarkable galaxy among trillions, life arose. And that life became conscious. And that consciousness learned to ask questions. And one of those questions, the deepest question, is the one we've been exploring together. What came before the beginning? We may never know with certainty, but we will never stop asking. And in that asking, in that refusal to accept mystery as final defeat, in that burning need to understand, we honor the universe that made us. We honor the minds that came before us. We honor the children who will come after us. And we take our place in the great chain of beings who have looked up at the stars and wondered. Close your eyes now. Let the questions settle into your mind like snow falling on still water. You don't need answers tonight. You only need rest. And perhaps as you drift away, as sleep takes you into its gentle dark, you'll dream. Dream of the universe. Dream of the void before. Dream of possibilities without end. And know that tomorrow, the questions will still be there, waiting, wondering, just like you. Good night, friend. Sleep well. The cosmos will be here when you wake.